Hello and welcome to Space Historians. I'm so glad you could join me tonight. This is a moment for us, a time to set aside the noise of the day, to breathe deeply, and to let our thoughts drift quietly beyond our world. Tonight, we are not in a hurry. We are gliding, letting the calm of the cosmos settle around us like a soft, familiar blanket. This is your time to simply be, to listen and to wonder. Before we begin our journey, I often think about where we all are, connected by this single story. Where in the world are you listening from right now? What time is it for you? It's a beautiful thought, isn't it, that while we may be separated by continents and oceans, the same stars are wheeling slowly overhead, watching over us all just as they watched over every generation that came before. If you enjoy these quiet voyages into cosmic history, a simple like and a subscribe help this channel find others who are also looking for a moment of peace and wonder. And for those of you who have already joined this growing community, thank you. Your presence here makes this shared journey possible. Each story we explore isn't just about planets or stars or the unimaginable distances between them. It's about the human stories held within that vastness, the ancient myths whispered under a dark sky, the patient discoveries that changed how we see ourselves, and the quiet, persistent questions that still echo in the silence. So tonight, as your breathing slows and your mind begins to settle, let these thoughts drift. Imagine the gentle pull of gravity easing. Imagine yourself floating, weightless, just at the edge of Earth's blue atmosphere. The familiar fades. The silence of space opens up before you. And there, stretching into infinity, is a canvas of light and time. Every shimmering star is a sun. Every sun, a story. If you gently press the notification bell, you'll always know when our next voyage is ready. But for now, you don't need to do anything at all. Just rest, breathe, and let the universe unfold. Let's travel together to the quiet side of the cosmos. When we stand under a truly dark sky, far from the glow of our cities, and look up, the sight is almost overwhelming. The night is not black. It is alive with light. Thousands of tiny, sharp pinpoints are scattered across the darkness, a shimmering dust of silver and blue. And for almost all of human history, that is all they were. Lights. They were decorations, gods, navigational aids, or perhaps, as some cultures believed, small holes poked in the dark curtain of night to let a divine light shine through. We told stories about them. We charted their slow dance across the seasons. We built calendars and temples around their motions. But what they were remained a mystery. They were cold, distant, and untouchable. They were, quite simply, the stars. And then, slowly, patiently, a new idea began to take hold. An idea that, at first, must have sounded impossible. An idea that was whispered more than proven. One that was so profound it was considered heresy. That idea was this. Every single point of light you see is a sun, not a symbol, not a candle, not a hole in the heavens. A sun. A real, burning, nuclear furnace, alive and blazing with energy. Each one is a world of its own, enormous and powerful, releasing more energy every second than our entire civilization has ever produced. Our sun, the one that warms our world and gives us life, is just one of them. It is not unique. It is one in a crowd of hundreds of billions. This is the impossible beginning of our story. The moment our perspective shifted forever. Because if every star is a sun, then the next question becomes almost inevitable. Do they also have planets? For most of our time on this world, the very concept of a solar system meant only ours. There was the sun, the earth, and the familiar planets we could see wandering against the fixed stars, lined up like marbles in a classroom diagram. That was the universe, as far as we knew it. Everything beyond that fragile boundary of sunlight was simply sky. The idea that those other suns, those distant, cold-looking stars, could have their own families of worlds was speculation, a philosopher's guess, a poet's dream. But the question stayed. Were we truly alone? Was our little arrangement of worlds the single, fortunate exception in a galaxy of solitary suns? Or was our solar system just one pattern among many, a blueprint repeated again and again across the Milky Way? Imagine standing in a dark field, centuries ago, staring up at that same sky. You would have no instruments, no space telescopes. You would have only your curiosity and the long, quiet patience of the night. The question would be there, but the answer would seem forever out of reach. Then, finally, after centuries of building better eyes, sharper tools, and larger mirrors, the universe began to answer, and the answer it gave us is, perhaps, the most astonishing fact we have ever learned. Planets are not rare. They are the rule, not the exception. We have only just begun to see them, to find the first faint hints of their presence, but our best estimates suggest that nearly every star in our galaxy has at least one planet. Many have more. This is a fact so large it is difficult to hold in the mind. Think of it this way. Our galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. If nearly all of them have planets, then the number of solar systems in our galaxy alone stretches into the hundreds of billions. We are talking about more planets than there are grains of sand on all the beaches of Earth. This is the hook, the impossible, vertigo-inducing truth. We thought we were the center of everything. Then we learned we were one planet around one star. And now we know we are one solar system among an uncountable, overflowing abundance of others. The night sky, which once seemed so empty, is full. It is saturated with worlds, worlds of rock and vapor, of ice and metal, worlds circling every kind of sun imaginable, from blazing blue giants to gentle yellow stars like our own, worlds with double sunsets, orbiting two stars at once, worlds so close to their suns that a year lasts only a few days, and others so far that their sun is just a bright spot in an eternal twilight sky. Our question tonight: how many solar systems are in our galaxy? Is not just a request for a number. It is a journey that changes how we see ourselves. It is the story of how we moved from believing we were a solo act to realizing we are part of a chorus of billions. So, let's begin that journey. Let's trace the path of that question from an impossible whisper in the dark to the quiet, revolutionary data that finally gave us an answer. Let's explore the worlds we have found, the ones we are still searching for, and the profound, humbling reality of what it means to be one of many. The next time you look up, let your eyes adjust. Every faint shimmer you see is a neighbor, a distant sun holding its own planets close, each one a miniature universe, a story of its own, waiting to be told. Our story begins, as all human stories do, right here, on Earth. It begins not with data or telescopes, but with a feeling. The feeling of being small under a vast, silent sky. For thousands of years, we have stood on this ground, tilted our heads back, and wondered. We are, by nature, a species that looks up, and in that act of looking up, We have always searched for meaning. The setting for our question is not an observatory or a lab. It is the dark fields of ancient Mesopotamia, where the first astronomers charted the heavens, believing the movements of the planets were messages from the gods. It is the stone circles of Europe, built to align with the sun and stars, a testament to a deep need to connect our lives on Earth with the rhythms of the cosmos. It is the deck of a Polynesian canoe, navigating the Pacific by the light of star paths learned by heart. For most of our history, the sky was a map for our lives. It told us when to plant, when to harvest, when to celebrate. The stars were our calendar, our compass, and our mythology. They were fixed, eternal, and perfect. And at the centre of this perfect, celestial sphere was us, Earth. This was the great story we told ourselves. The sun, the moon, and the 5 wandering stars we called planets all moved around our world in complex divine circles. This was a comforting, orderly universe. It had structure, and we were at its very heart. Everything was as it should be. But the human mind is restless. It asks difficult questions, and as our tools for observing became just a little better, cracks began to appear in that perfect story. In the early 1600s, a man named Galileo Galilei pointed a new invention, the telescope, at the planet Jupiter. And he saw something that should not have been there. He saw 4 tiny lights circling Jupiter itself. Moons. If Jupiter had moons, then not everything in the heavens orbited the Earth. The old story was wrong. This was a terrifying and thrilling realization. It demoted us. It shifted us from the center of everything to just another planet. And if Earth was a planet and the sun was just a star, the implication was staggering. This is where our story truly begins to take shape, in the minds of the philosophers who dared to follow that logic. If our star had planets, why not others? In the late 1500s, a philosopher in Italy named Giordano Bruno travelled Europe, speaking of a radical, infinite universe. He argued that the stars were other suns, and that they too must have their own worlds, their own Earths, perhaps even their own life. This idea was not just speculation, it was a philosophical awakening, but it was also a dangerous one. To suggest that our world was not unique, to fill the heavens with countless other worlds, was to challenge the very foundation of divine authority. For his ideas, Giordano Bruno was declared a heretic, and, in the year 1600, he was burned at the stake. The setting for our question, then, is one of human courage and human fear. The fear of losing our special place in the cosmos, and the courage to seek the truth anyway. Even after Bruno, the idea did not die. It lived on, quietly, at the edges of astronomy. Scientists and poets alike dreamed of this plurality of worlds. They imagined what life might be like on planets circling other stars. But they had no proof. It remained a guess, a beautiful and poetic speculation. Science, after all, needs evidence, and the universe does not give up its secrets easily. For centuries, that is where the story stalled. We built larger telescopes. We discovered new moons around Saturn, phases of Venus, and new planets in our own solar system. We mapped the stars with incredible precision, but those other worlds remained stubbornly invisible. They were too small, too faint, and too hopelessly lost in the blinding glare of their parent stars. You cannot just point a telescope and see a planet orbiting a distant sun. It is like trying to spot a firefly sitting next to a lighthouse from miles away. The human element of our story is this deep, aching desire to know, set against the immense difficulty of finding out. We were trapped by distance and by light. So, scientists had to get clever. They had to stop looking for the firefly and start looking for the tiny, almost imperceptible effect the firefly has on the lighthouse. They realized that if a planet was orbiting a star, its gravity, though small, would still pull on the star. A star with a large planet would not sit perfectly still. It would wobble. This was the new investigation, not to see other worlds, but to detect their invisible gravitational tug. For decades, astronomers searched for these tiny wobbles. They pointed their instruments at nearest stars night after night, measuring their light, looking for a subtle shift in the pattern. It was slow, painstaking, and often frustrating work. Some astronomers in the 20th century claimed they had found such wobbles, but the claims never held up. The signals were too faint, the technology not quite ready. For a long time, the universe seemed to belong to us alone. But the setting was changing. Our technology was catching up to our imagination. We were building spectrographs of incredible precision, tools that could measure the colour of starlight so accurately that a movement of just a few meters per second could be detected. We were no longer just looking at the sky, we were listening to it, listening for a rhythm, a pattern, a faint wobble in the dance of a star that would tell us it was not dancing alone. And in 1992, from a place no one expected, the first definitive signal finally came through. The first confirmed discovery of another solar system did not happen with a triumphant shout in the middle of the night. It was not the kind of moment you might imagine, with an astronomer looking through a giant telescope and suddenly seeing a tiny, new world gleaming beside a distant star. The truth arrived quietly. It was buried in data, in a stream of numbers from a place in the cosmos so strange and so violent. It was the last place anyone on Earth would have thought to look for planets. The discovery was made at a cosmic graveyard. The object of study was not a bright yellow sun like ours. It was a pulsar. A pulsar is the collapsed hyperdense core of a massive star that died long ago in a fiery explosion called a supernova. What remains is a sphere barely 20 kilometers across, yet it contains more mass than our entire sun. It is a neutron star, spinning incredibly fast, some rotating hundreds of times every second. As it spins, it shoots out beams of intense radiation, like a cosmic lighthouse. For astronomers on Earth, these beams are not seen, but heard as radio pulses. And these pulses are precise. They are, quite literally, the most accurate clocks in the known universe. Their rhythm is so perfect that you can predict the arrival of a pulse years in advance, down to a fraction of a millisecond. It is this very precision that makes them perfect tools for finding anomalies. If anything at all is pulling on that pulsar, even slightly, its rhythm will change. The clock will skip a beat. In 1992, two astronomers, Alexander Wolszczan and Dale Frail, were studying the radio signals from one such pulsar, known as PSRB 1257+12. It was just another object in their survey, a dead star spinning 30 times a second, its lighthouse beams sweeping past Earth with perfect metronomic regularity. Or rather, almost perfect. Wolszczan noticed tiny irregularities in the timing of the pulses. They were arriving just a fraction of a second too early, then a fraction of a second too late. At first, he assumed it was just noise, a glitch in the telescope, or interference in the data. This kind of faint signal was almost always an error, but he kept checking. And as he analysed the data more carefully, he saw that the variations were not random at all. They had a pattern. The pulses would speed up and slow down in a steady repeating cycle. Something was pulling on this dead star, tugging it back and forth as it spun. When they did the calculations, the answer was astonishing. The pattern of the wobble could only be explained by the gravitational pull of planets. Not just one, but two of them, orbiting the pulsar in steady, predictable paths. Later, a third, smaller planet would be confirmed. This was it. The first confirmed discovery of worlds beyond our own solar system. And they were in the most impossible, inhospitable place imaginable. These were not serene worlds. They were orbiting the remnant of an apocalypse. They were bathed in radiation so intense it would destroy any known form of life. How did they get there? Were they the charred survivors of the original star's family, somehow clinging to existence after the supernova? Or were they new worlds, formed out of the dust and debris of the explosion itself? A kind of second, zombie solar system rising from the dead. The discovery sparked a profound new mystery. It was a quiet, mathematical revelation that landed with the force of a thunderclap. For the first time in human history, we knew. We were not alone in having a solar system. The galaxy was capable of making them elsewhere. And if planets could exist here, in the cold, irradiated graveyard of a dead star, then they could exist almost anywhere. The calm of our old assumptions was broken. The universe was far stranger and far more creative than we had ever dared to believe. The hunt was no longer a philosopher's dream. It was real. The discovery of the pulsar planets in 1992 was a profound moment for human knowledge. It was the first time we could definitively say, yes, other solar systems exist. But the human response, both from the public and the wider scientific community, was not one of immediate celebration. It was quiet, cautious, and tinged with a deep sense of strangeness. After all, these were not worlds in the way we dreamed of them. They were orbiting a dead star, a tiny spinning corpse blasting out radiation. It was a zombie solar system. It proved a mathematical point, but it lacked romance. It didn't feel like a neighbour. It felt like a curiosity, an anomaly from a cosmic horror story. It didn't make front-page headlines. Furthermore, astronomers had learned to be skeptical. For decades, the search for other worlds had been haunted by false alarms. Several times in the 20th century, respected astronomers had claimed to see the telltale wobble of a planet, only to have the data fall apart under closer scrutiny. Science had been burned before, so, while the pulsar data was solid, it was filed away as a fascinating but isolated fact. The galaxy had shown us it could make planets, but it had done so in a way that seemed to have no connection to our own existence. The real, human, emotional response, the one that changed everything, came 3 years later. In 1995, the announcement came from two Swiss astronomers, Michel Mayor and Didier Queloz. They had been patiently watching a star called 51 Pegasi. This was not a dead pulsar. This was a star like our sun, a living, breathing yellow star just 50 light-years away in the constellation Pegasus. This felt, as they said, closer to home. And it was wobbling, but when they analysed the wobble, the data made no sense. It was impossible. The star's light was shifting back and forth in a steady rhythm, but it was happening incredibly fast. The pattern revealed a planet, a massive one, at least half the mass of our own Jupiter, but it was orbiting its star in just 4 days. This was the first response. Sheer, profound disbelief. It was not awe, it was confusion. The planet, 51 Pegasi b, was orbiting so close to its star that its atmosphere was being scorched, with surface temperatures hot enough to melt metal. It was orbiting its sun at a distance 8 times closer than Mercury orbits ours. This planet should not have existed. For our entire history, we had only one blueprint for how a solar system worked, our own, and our blueprint was clear. Small, rocky planets formed in the hot inner region. Large, gas giants formed in the cold, outer regions, far beyond the asteroid belt, where ice could survive and accumulate. That was the rule. It was the only way we knew how to build a world like Jupiter. This discovery did not just add a new world to our maps. It took our map, our blueprint, our entire understanding of how solar systems form, and tore it to pieces. This was the contradiction. This was the moment science stared at mystery. First response was to assume the data was wrong. Mayer and Queloz themselves checked their data for months, convinced it had to be a mistake. But the signal was clean, it was consistent, it was unmistakable. When they finally announced it, the scientific community reacted with the same skepticism they had shown before. They checked. They double-checked. They debated. But this time, the evidence held. Other teams quickly pointed their own telescopes at 51 Pegasi, and they saw it too. The planet was real. The disbelief and confusion slowly, over weeks and months, turned into a profound, earth-shaking awe. The tone of the entire field of astronomy changed. The discovery of the pulsar planets had been a whisper. This was a trumpet blast. It told us not only that other solar systems existed, but that they could be wildly, fundamentally different from our own. It meant our single, precious blueprint was not the rule. It was just one of countless variations. The universe, it turned out, was far more creative, more chaotic, and more inventive than we had ever allowed ourselves to imagine. This was the moment the hunt truly began. This was the moment that built authenticity. It showed us that nature did not care about our rules. The discovery of 51 Pegasi b, the hot Jupiter, ignited a global effort. Observatories around the world began upgrading their instruments, pointing them at hundreds of stars, all of them asking the same thrilling new question: if that is out there, what else have we been missing? The discovery of 51 Pegasi b was more than just a discovery. It was a contradiction, a paradox delivered to us from 50 light-years away. It created a deep philosophical tension that cut to the very heart of how we saw the universe and our place within it. For centuries, our science of the cosmos was built on a single, fundamental assumption that our solar system was the blueprint. It was the only one we had. We looked at its structure, and it seemed to make perfect, elegant sense. It was orderly. It was neat. We believed we understood the rules of its creation. In the beginning, a star forms from a collapsing cloud of gas and dust. Around it, the leftover material flattens into a vast, rotating disk. The new star's heat and wind blast through this disk, creating a natural divide. Close to the star, it is too hot for ice to survive. Only heavy materials like rock and metal can condense. This is where small rocky worlds like Mercury, Venus, Earth, and Mars are born. Then, farther out, beyond a critical boundary called the frost line, the universe changes. Here, it is cold enough for water, methane, and ammonia to freeze into solid ice. Ice is abundant, and it acts like a cosmic glue, allowing material to build up quickly. This is where the giants are born. Massive cores form and grow so large that their gravity pulls in vast, thick envelopes of hydrogen and helium gas from the disk. This, we believed, was how Jupiter and Saturn came to be. This was our model. It was clean, logical, and it explained our home perfectly. Small, rocky planets in, giant, gassy planets out. This was the rule. And 51 Pegasi b broke that rule in every way imaginable. It was a gas giant, as big as Jupiter, yet it was not in the cold, outer regions of its system. It was huddled next to its star, orbiting 8 times closer than Mercury orbits our Sun. It was a hot Jupiter. According to our science, according to our perfect blueprint, this planet was impossible. It simply could not exist. A gas giant could not form that close to a star. The heat would have vaporized its icy materials. The star's gravity would have made it difficult to gather that much gas. It was a contradiction in terms, a mystery staring back at us through our own data. This was the paradox. For the first time, our science, which had been so successful in explaining our own home, was completely and totally wrong about someone else's. This forced a profound and uncomfortable reckoning. Astronomers had to face 2 possibilities. Either our entire, cherished theory of how planets form was fundamentally flawed, or something else was at play. Something chaotic, something violent, something we had never thought to include in our neat, orderly models. This is where the mystery deepened. What if planets don't stay where they are born? This was the birth of a radical new idea, planetary migration. Scientists began to wonder, what if 51 Pegasi b had formed in the cold, outer regions of its system, just as our theories predicted? But what if, in the chaos of that system's youth, something had disturbed it? What if gravitational tugs from the disk, or from other unseen planets, had caused its orbit to decay? What if this giant world had begun a long, slow spiral inward, moving from its birthplace, crossing the frost line, and finally settling into the scorching hot orbit where we found it? This idea was thrilling, and it was terrifying, because it meant that solar systems were not the static, clockwork, permanent structures we had always imagined. They were not neat diagrams in a textbook. They were dynamic, living, and evolving systems. They could be chaotic. Planets could move, collide, swap orbits, or even be ejected entirely into the lonely darkness of interstellar space. This was the new philosophical tension. If 51 Pegasi b had migrated, it meant that the final arrangement of a solar system was not a guarantee. It was the result of a long, violent, and unpredictable history. It also opened a second, even deeper mystery. If systems are this chaotic, and a giant planet like Jupiter can spiral inward, what would happen to the small rocky worlds the Earth's in its path? A migrating giant would be a wrecking ball, clearing its path, flinging smaller planets into its star or out into the void. This one single discovery raised a chilling possibility. Maybe the reason our solar system looks the way it does, with Jupiter far away, is not because it's normal, but because it's lucky. Maybe our system is the exception. Maybe the calm, stable orbits that allowed life to evolve here are actually rare. The universe was no longer a collection of predictable, orderly copies of our home. It was a vast, cosmic workshop where nature was inventive, playing by rules we had not yet learned. 51 Pegasi b was our teacher. It was the mystery that forced us to let go of our assumptions, to accept that nature was far more complex and creative than we had ever known. We thought we had the blueprint, but the universe had just shown us that it had countless others. The discovery of 51 Pegasi b, the hot Jupiter, had turned our neat models of the universe upside down. It opened the door, proving that other solar systems were not just possible, but that they were wildly, unimaginably diverse. And once that door was opened, the investigation truly began. The trickle of discoveries became a small stream. Using the wobble method, now called the radial velocity technique, teams around the world found dozens of new planets. But as the catalogue grew, a new, more subtle problem emerged. The planets we were finding were almost all giants. They were massive worlds like Jupiter or Saturn, orbiting close to their stars. We found them because they were the easiest to find. A massive planet gives its star a powerful gravitational tug, creating a large, obvious wobble. We were, in essence, only hearing the loudest systems in the cosmic orchestra. We were finding the monsters, but the real question, the one that hummed quietly beneath all of human history, was not, are there other Jupiters? The question was, are there other Earths? And for that question, the wobble method was not sensitive enough. An Earth-sized planet is thousands of times less massive than a Jupiter. Its gravitational pull on its star is impossibly small. It creates a wobble of only a few centimeters per second, a signal so faint it was, completely lost in the noise. Our investigation had hit a wall. We knew the galaxy was full of worlds, but the ones we truly cared about, the small, rocky, quiet planets, remained hidden. We needed a new way to look, a new, more patient, and more precise method of investigation. This is when astronomers turned to an idea that was simple in concept, but phenomenally difficult in practice. It was called the transit method. The idea was this. If a planet's orbit happens to be lined up perfectly, edge on from our point of view, it will pass directly in front of its star. When it does, it will block a tiny, almost imperceptible fraction of the starlight. It would be a miniature eclipse, a brief, faint shadow. If you could build a telescope sensitive enough to measure that tiny dip in brightness, and if you saw that dip repeat once, twice, 3 times, all with perfect, clockwork regularity, you would know you had found a planet. This was the new investigation. It was a search not for a wobble, but for a shadow. The precision required was breathtaking. The dimming caused by a Jupiter-sized planet crossing its star would be about 1%. That was already difficult to measure, but the shadow cast by an Earth-sized planet would be minuscule, a dimming of less than 1 part in 10,000. It was, as one scientist put it, like trying to detect a gnat flying in front of a single distant streetlight from miles away. To do this, you would need a telescope that was perfectly stable. It couldn't be on Earth, because our own shimmering, wavering atmosphere would blur the starlight and drown out the signal. It had to be in space, and it couldn't just glance at stars. It had to stare. It would need to fix its gaze on one single patch of sky and not blink, not even for a moment, for years. This was the action that turned our curiosity into one of the great explorations of our time. This was the genesis of NASA's Kepler Space Telescope. Kepler was designed for this single, profound mission. It was a $900 million machine built for one purpose: to stare. It was launched in 2009, not into orbit around Earth, but into an orbit that trailed behind the Earth, following our planet around the Sun. This kept it stable, away from Earth's interference, allowing it to maintain its steady, unblinking gaze. Its target was a single, unremarkable patch of sky in the constellations Cygnus and Lyra. It was an area of the sky so small it would take 400 of them to cover the whole. But within that one tiny window, there were over 150,000 stars. Kepler's mission was not to find one or two planets. Its mission was a statistical census. It was built to answer the big question. It would stare at those 150,000 stars all at once for 4 years straight. It would measure their brightness with exquisite care every 30 minutes, looking for those tiny, repeating shadows. By the end of its mission, we would finally have an answer. We would be able to say, with certainty, what fraction of stars in our galaxy have planets. And, most importantly, we would know how many of them, just in that one small sample, were the size of Earth. The investigation was now fully underway. The quiet, patient observer was in place. All humanity had to do now was watch and wait for the shadows to come in. For 4 years, the Kepler Space Telescope drifted silently, trailing Earth, its gaze fixed on that one small patch of the cosmos. It watched, without blinking, 150,000 stars. It was a mission of profound patience, a quiet, technological meditation. Kepler was not looking for worlds. It was looking for the shadows of worlds. And as its long watch continued, the data began to stream back to Earth. At first, it looked like noise. Stars are not perfect. Static lights. They flicker, they pulse, they boil with magnetic storms and dark spots on their surfaces. Kepler's data was a chaotic jumble of these natural variations. But buried within that noise were the signals humanity was waiting for. Scientists and computer algorithms began the painstaking work of sifting through the light of all 150,000 stars, looking for the telltale clue, a tiny, periodic dip in brightness. A single dip meant nothing. It could be a star spot, an instrument glitch, or another star passing behind. But when that same dip, with the same depth and the same duration, repeated itself, once, twice, 3 times, all with the precision of a clock that was not noise, that was an orbit, that was a planet. Within the first few months, Kepler had identified hundreds of these planetary candidates. Within a year, the number had climbed into the thousands. The data was overwhelming. It was a deluge. Each signal was a faint knock from across the universe, a hint of another system, unseen but real. The clues and fragments pouring in from Kepler were not just confirming that planets existed. They were revealing, for the first time, the sheer, breathtaking abundance of them. The data showed that our galaxy was teeming with hidden families. It became clear, with a statistical weight that was impossible to ignore, that planets were not rare exceptions. They were, in fact, practically guaranteed. The data became a torrent, and it began to paint a picture of the galaxy that no one had ever seen before. Thousands of planets revealed themselves. Some were giants, like the hot Jupiters we had found before, but they were the minority. What Kepler truly found, in overwhelming numbers, were worlds that our own solar system doesn't even have. The most common type of planet in our galaxy, it turns out, is a world called a super-Earth. These are planets larger than Earth but smaller than Neptune, worlds of rock and ice, perhaps with thick atmospheres or deep oceans. They are everywhere. Our solar system, by not having one, suddenly looked a little less normal. And then there were the smaller worlds. Kepler began to find planets the size of Earth, and even smaller. Its data was so precise it could spot worlds the size of Mars. These were the clues we had truly been searching for. As astronomers analysed the patterns, new architectures emerged. We found systems that defied imagination. There were planets in multiple star systems, orbiting 2 suns at once, experiencing double sunsets just like the ones from our science fiction dreams. Kepler found planets locked in perfect orbital resonance, their gravitational pulls keeping them in a delicate, synchronized dance. It found systems packed with planets, like TRAPPIST-1, with 7 rocky worlds all orbiting closer to their star than Mercury orbits our Sun. The data was a revelation. Suddenly, we were not just asking whether other solar systems existed, we were cataloguing them, we were comparing them. We were, for the first time, beginning to understand our place in the galactic family. And the data held one final, profound fragment. As scientists sorted the thousands of candidates, they began to find them in the Goldilocks zone, the temperate region around a star where conditions are just right for liquid water to exist on a planet's surface. In 2011, the team announced Kepler 2b, a planet about twice the size of Earth, orbiting squarely within its star's habitable zone. It was the first solid evidence that potentially habitable worlds were not just a fantasy. Soon, others followed. Kepler 1.8, 6f, an Earth-sized world in a cooler orbit. Kepler 452b, a slightly larger cousin to Earth orbiting a star very much like our Sun. This was the data that changed history. For centuries we had wondered if there were other Earths. Philosophers had dreamed of it, scientists had hypothesized it. Now, the data from Kepler's long, quiet stare gave us the answer. Yes, they are out there. They are not rare. They are common. Our world is just one among billions. The Kepler data was a flood. It didn't just add to our catalogue of worlds. It forced us to rethink what a solar system even was. The neat, orderly model we had grown up with, small rocky worlds in, large gas giants out, all in stable circular orbits, was not a universal blueprint. It was just our story, and as the data poured in, it became clear that the galaxy was a far more creative, chaotic, and imaginative architect than we had ever been. Our minds had to divide. We had to let go of the old, comfortable theories and embrace a new, wilder reality. The universe, it seemed, was a cosmic laboratory, and it had run every experiment imaginable. One of the first and most stunning new theories to emerge from the data was something long relegated to science fiction. A world with 2 suns. For decades, we had imagined what it would be like to stand on a planet like Luke Skywalker's Tatooine, watching a double sunset. But most astronomers believed such systems would be too unstable for planets to even form, let alone survive. The complex, warring gravitational pulls of 2 stars would, in theory, tear a forming disk apart or eject any new planets into the cold of space. And then, Kepler found Kepler 1.6b. It was a real, confirmed planet, orbiting 2 stars at once. The stars orbited each other, and the planet orbited both of them, like a cosmic dance where the suns circle each other while the planet moves around them both. This discovery was a triumph of observation over theory. Nature, it turned out, doesn't avoid complexity, it embraces it. Suddenly, a whole new category of solar systems was unlocked. We now know of many such circumbinary planets. From their surfaces, the sky would be alien and beautiful. 2 suns would rise and set, sometimes together, sometimes apart, casting shifting shadows and creating seasons we can barely imagine. This was just the beginning of the new cosmic zoo. As Kepler stared, it found systems that were the complete opposite of ours, not vast and sprawling, but impossibly compact, like miniature clockworks. The most famous of these is a system called TRAPPIST-1, just 40 light-years away. It is a tiny, cool, red dwarf star, and orbiting it are 7 rocky planets, all roughly the size of Earth. The astonishing part is their spacing. All 7 of them are packed into orbits smaller than Mercury's orbit around our Sun. If you were standing on one of these worlds, the others would not be faint stars in the sky. They would appear as large as, or larger than, our own moon. You could watch them glide overhead, their phases changing, their continents or oceans visible. But this, too, presented a contradiction. How could such a system possibly be stable? With so many worlds packed so closely, their gravity should tear each other apart, sending them scattering in a matter of centuries. The data revealed a beautiful, elegant new theory: resonance. The planets of TRAPPIST-1 are locked in a perfect gravitational harmony. For every 8 times the innermost planet orbits, the next one orbits 5 times, the next 3, and so on, in a precise mathematical chain. This steady, repeating rhythm, this gravitational dance, is what keeps the whole fragile system from collapsing. It is a solar system built not on wide open spaces, but on perfect timing. And then, Kepler found the survivors. We had always assumed orbits were neat and circular, but the data revealed planets in wildly eccentric, elongated paths, worlds that swing in close to their stars for a brief, scorching summer before flying far out into the frozen darkness. We even found planets orbiting backwards, spinning in the opposite direction of their star's rotation. These systems told a different story, not one of quiet formation, but of a violent and chaotic past. These are the battle-scarred solar systems. They are the likely survivors of gravitational upheavals, where planets may have collided or been ejected, leaving the remaining worlds in tilted, battered, and strange orbits. This is where our minds truly had to divide. We had to accept that our solar system, with its stable, nearly circular orbits and its wide, peaceful spacing, might not be the norm at all. Our calm little corner of the galaxy might be the exception. The galaxy, as a whole, is a place of extremes. It builds compact, resonant clockworks. It builds chaotic, eccentric survivors. And it builds stable, Tatooine-like worlds around 2 suns. The old theory of one simple blueprint was gone. The new reality was that there is no blueprint. There is only a vast, creative, and unending experiment. The Kepler telescope, in its long, silent watch, had opened up a cosmic zoo. It revealed a galaxy filled with strange and wonderful architectures. Worlds with 2 suns, compact systems of rocky planets, and eccentric giants on wild, chaotic orbits. We had discovered that nature's imagination was far broader than our own. We had proven that the galaxy was, without a doubt, full of solar systems. But this was not the true, underlying question, was it? The human heart does not ask, are there hot Jupiters? The human heart does not wonder, how many worlds orbit backwards? For all of our history, from the first person who looked up at the stars, the question has always been simpler and far more profound. Are we alone? Is there anywhere else like here? This was the deeper mystery. Beyond the statistics, beyond the catalogue of strange new worlds, we were searching for a reflection. We were looking for a home. We were looking for another Earth. To find it, astronomers had to narrow their search. They had to filter the thousands of new planets through a new, much finer lens. This lens had a name that sounded almost like a fairy tale. It was called the Goldilocks Zone. The name comes from the old story of a girl who finds 3 bowls of porridge. One is too hot, one is too cold, and one is just right. In astronomy, this describes a narrow, delicate region around every star where the temperature is neither too high nor too low. It is the one place where the energy from the star is gentle enough to allow for the most precious substance we know: liquid water. Water is the foundation of everything we call life. It dissolves, it transports, it moderates. Every living thing on our planet depends on it. So, when we search for habitable planets, water is our benchmark. We are not looking for planets, necessarily. We are looking for oceans. This just right zone is a fragile balance. It is a distance, not a place. Around a bright, hot star, the habitable zone lies far out, distant and wide. Around a cool, dim star, like a red dwarf, the zone huddles in close for warmth. We know this balance intimately from our own home. Our solar system is the perfect example. Venus, our neighbour, orbits just inside this zone. It is too close. Any water it may have had boiled away long ago, creating a runaway greenhouse effect that turned its surface into a furnace hot enough to melt lead. Mars, on the other side, orbits just beyond the zone. It is too cold. Its thin air cannot hold the sun's warmth, and any water it once had is now locked away as ice under a dry, frozen desert. And then there is Earth, in the middle. Not too hot, not too cold, just right. This was the deeper mystery Kepler was built to solve. Were there other planets, in other solar systems, orbiting in their Goldilocks zone? The investigation shifted. Scientists were no longer just counting shadows. They were measuring them. From the depth of the shadow, they could tell the planet's size. From the timing of its orbit, they could tell its distance from its star. And with those two pieces of data, they could find the one thing they were looking for. They could find the small rocky worlds orbiting in the just right zone. The data, which had already been a flood, now became a revelation. In 2011, the Kepler team announced the discovery of Kepler-2, 2b. It was a planet roughly twice the size of Earth, orbiting a star very much like our Sun, and it was orbiting squarely in the middle of its star's habitable zone. This was not a gas giant. This was not a scorched world. This was the first solid candidate for a water world. It was not Earth's twin, but it was the first glimpse of a possibility. A place where oceans could, in theory, exist. And once the first one was found, others soon followed. There was Kepler 62f, a world just a little larger than Earth, orbiting a star cooler than our Sun. Then Kepler 186f, the first truly Earth-sized planet found in the habitable zone of its star. And then Kepler 452b, a super-Earth in a long orbit circling a sun-like star, a true cousin to our own world. This was the something bigger. This was the hidden truth beneath the surface. The galaxy was not just full of planets. The data from Kepler proved, for the first time in human history, that the galaxy is also full of potential homes. For centuries, we had wondered, we had dreamed, we had looked up at the stars and asked if there were other Earths. The answer was no longer a guess, or a philosopher's hope. It was data. It was statistics. The answer was yes. They are out there. They are not rare. They are common. Our world is one of billions. The night sky, which had once seemed so cold and empty, now shimmered with a new and deeper meaning. It was not just a map of suns. It was a map of possibilities. The discoveries were piling up. Jupiters in scorching orbits, worlds with two suns, compact systems of rocky planets, and most profoundly, Earth-sized worlds in just right orbits. The Kepler data had provided what was once unimaginable, a catalogue of other solar systems, a cosmic zoo of possibilities. But as scientists, astronomers, and philosophers sifted through this mountain of data, a deeper, more fundamental realization began to emerge. This was the true turning point. It was not a single discovery. It was not one more planet added to the list. It was the statistical, undeniable, and world-changing weight of all of them combined. It was the moment the census was finally tallied, and the result was this. Planets are not rare. They are not the exception. They are the rule. They are the natural, inevitable, and standard outcome of a star being born. For all of human history, we had looked up at the night sky and assumed emptiness. We saw ourselves as a tiny, miraculous accident, a single, complex system of worlds that had somehow beaten the impossible odds, a fortunate island of order in an infinite, sterile void. This was the moment that belief shattered forever. The Kepler data, when extrapolated to the entire galaxy, was unambiguous. It showed us, with a confidence that was almost dizzying, that nearly every star in the Milky Way has at least one planet. Many, if not most, have more. This was the transformation. The old question, the one that had haunted us for millennia, do other solar systems exist, was now officially dead. It had been answered not just with a yes, but with a yes everywhere. The question was no longer if. The question had changed forever. The new questions were far more profound. How many? What kinds? And if planets are everywhere, how common is life? This realization is the peak of our journey. It is the moment the tension breaks and our entire worldview shifts. The data pointed to a staggering conclusion. There are, statistically, more planets than there are stars in our galaxy. Stop and let that thought settle. There are an estimated 400 billion stars in the Milky Way, and there are more planets than that. We are talking about, quite possibly, 1 trillion worlds. More planets in our one galaxy than there are grains of sand on all the beaches of our one world. Suddenly, the universe was not a lonely place. It was a crowded one. This turning point forced us to understand why, and the answer was as simple as it was elegant. Nature does not like to be wasteful. When a star is born from a collapsing cloud of gas and dust, it is messy. The material that doesn't fall into the star flattens into a vast spinning protostellar disk. This disk is not an accident. It is a given. And in that disk, gravity, time, and chemistry get to work. Dust becomes rock, and rock becomes worlds. Planet formation, we realized, is not a rare miracle. It is the galaxy's standard manufacturing process. Where there are stars, there will be disks. And where there are disks, there will almost always be planets. This is the Great Awakening. We are not an exception to the rules of the cosmos. We are the evidence of them. Our solar system is not a rare treasure, unique in all the universe. It is a local example of a universal phenomenon. This changed our perspective on ourselves. It was the final step in a long, humbling journey. First, we learned the Earth was not the center of the solar system. Then, we learned our sun was not the center of the galaxy. Now, we learned that our entire solar system is not the center of creation, but just one of billions, a single, ordinary family in a city of stars. This was the climax of the investigation. The galaxy, which had once seemed like a dark, silent ocean, was now revealed to be a coral reef teeming with unseen structures, overflowing with worlds. The implications were staggering. If there are hundreds of billions of solar systems, and if Kepler's data was right, that meant there were tens of billions of planets just like Earth, orbiting in the just right zone. The silence we had been listening to for centuries was not the silence of an empty, sterile void. It was the silence of an abundance we were not yet equipped to see. The turning point was this. We finally understood that the sky above us is not empty. It is, quite simply, full. The turning point was profound. We had learned that our galaxy is not a lonely void, but a teeming metropolis of worlds. This realization that solar systems are the rule and not the exception had an immediate and powerful consequence. It forced us to ask a new, far more practical question. If the galaxy is a planet factory, then how does it work? If nature makes worlds as commonly as trees make leaves, what is the process? What is the recipe? The consequence of knowing that they exist was the urgent need to understand how they are made. And to do that, we had to journey in our minds to a place of both chaos and quiet beauty. The cosmic workshop where planets are born. Our story now moves into the dark. It begins deep inside the spiral arms of our galaxy, in vast, cold, and lonely clouds of molecular hydrogen and dust. These clouds are enormous, stretching for dozens of light years, and they are the raw material for everything that is to come. Inside these dark nurseries, gravity begins its slow, patient work. Small pockets of gas and dust, perhaps disturbed by a passing star or the shock wave from a distant supernova, begin to collapse in on themselves. As a clump falls inward, it spins, faster and faster, just as a figure skater spins faster when they pull in their arms. This spinning motion flattens the collapsing cloud into a vast rotating disk. At the very center of this disk, the pressure and temperature build until it becomes so immense that hydrogen atoms fuse together. A new star ignites, but this star is only the beginning. The real consequence is what's left behind, the disk itself. This is the protostellar disk, and it is the birthplace of worlds. It is a swirling, turbulent mist of gas and tiny grains of silicate, ice, and metal, all orbiting the newborn sun. And it is here, in this spinning cloud, that the recipe for a solar system unfolds. The process is one of quiet, patient construction. It starts small, microscopic dust grains, coated in sticky ice, collide and stick together. Then those clumps stick to other clumps. Dust becomes pebbles. Pebbles become rocks. Rocks grow into larger bodies, kilometers wide, which we call planetesimals. It is a slow, precarious ballet. If the collisions are too fast, the objects shatter. If they are too slow, they just bounce apart. Only in a just right range of speeds can they merge and grow. But as these planetesimals grow, a few get a powerful advantage. They become large enough that their own gravity starts to dominate, pulling in more and more material, sweeping their orbits clean. These are the seeds of planets. And now, the recipe reveals its most important step. The new star's heat blasts through the disk, creating a great divide. It's a boundary we call the frost line. Close to the star, it is too hot. All the ices, water, methane, ammonia evaporate into gas. The only things that can survive as solids are rock and metal. Because these materials are rare, the planets that form here grow more slowly and remain small and dense. This is the origin of the inner, rocky worlds, like Mercury, Venus, Earth, and Mars. But beyond the frost line, The universe is different. Here, it is cold enough for all those ices to remain frozen solid, and ice is incredibly abundant. This allows the forming cores to grow massive incredibly quickly. A core can reach 10 times the mass of Earth in a relatively short time, and once it reaches that critical mass, its gravity is so powerful it begins to pull in vast, thick envelopes of hydrogen and helium gas from the surrounding disk. This is the consequence. This is how the giants are born. Jupiter and Saturn, in our own system, are worlds that formed beyond the frost line, growing fat and heavy on the abundant gas and ice before the young sun's solar wind blew the disk away. This, we realized, is the ripple effect of our discovery. We were not just finding planets, we were finding the physical evidence of this universal recipe. The hot Jupiters that had so confused us were the consequence of this process going wrong, of a giant planet migrating from its cold birthplace. The small rocky worlds Kepler found in the habitable zone were the consequence of this process going right, of worlds forming in the temperate rocky region and staying there. The galaxy, it turns out, is a factory that runs on a simple, elegant assembly line, repeated billions of times over. Clouds collapse, disks form, dust turns to rock, and rock turns to worlds. The impact of this new knowledge that the galaxy is a factory for worlds was not just scientific. It was personal. It echoed through time, changing not only how we see the stars, but how we see ourselves. For our entire history, we had one model for a stable, life-bearing solar system, our own. We looked at its neat, orderly design as the very definition of normal. It was our cosmic blueprint, the one we assumed nature would use again and again. The thousands of new solar systems discovered by Kepler and other surveys showed us that nature has no single blueprint. This was the true impact. Our normal was not normal at all. In fact, our solar system is looking stranger and stranger all the time. Think of it. The Kepler data showed that the most common type of planet in the galaxy is the super-Earth, a world larger than ours but smaller than Neptune. We do not have one. The data showed that compact systems, with many planets huddled close to their star, are common. We do not have that. The data showed that hot Jupiters, while not the majority, are a frequent outcome of planetary formation. We do not have one of those either. Suddenly, our home began to look unusual. Our system, with its wide, stable, nearly circular orbits, and its clear division between small rocky worlds and distant gas giants, is just one of countless variations. And it may, in fact, be one of the rarer ones. This discovery reshaped our collective understanding of our own history. We began to look at our solar system not as a static, finished piece, but as the survivor of a long and violent past. We now believe that our own system was not always this calm. The new models, born from the chaos we saw in other systems, suggest that our own giants, Jupiter and Saturn, may not have stayed put. They likely migrated too. In a model known as the Grand Tack, Jupiter may have spiraled inward, closer to the Sun, before Saturn's gravity pulled it back out. This giant, sweeping motion, like a cosmic wrecking ball, would have cleared the inner solar system, explaining why Mars is so small and why there are no super-Earths here. In this new story, our stability is not a given. It is a fortunate accident. It is the result of a gravitational dance that happened billions of years ago. A dance that could have gone another way. If Jupiter had migrated inward and stayed there, like 51 Pegasi b, it would have scattered the forming inner planets. There would be no Mercury, no Venus, and no Earth. This is the echo that travels through time. The discovery of other worlds forced us to rewrite the story of our own. We are not the template. We are the outlier. We are the quiet, orderly exception that survived a chaotic process. This realization connects our individual existence to the grand, collective history of the galaxy. The fact that we are here, breathing, wondering, and looking up at the stars is the direct result of a specific and perhaps rare set of gravitational interactions that left our planet in a stable and temperate orbit for billions of years. This new perspective changed everything. The search for Earth-like planets became more urgent and also more humble. We are no longer looking for copies of ourselves, assuming they are everywhere. We are, instead, searching for other places that might have won a similar cosmic lottery, other places that found a way to achieve long-term stability in a galaxy that is fundamentally chaotic. This is the legacy of the Kepler mission. It did not just give us a number, it gave us context. Every time we look up at the night sky now, we see it differently. We are not a lonely miracle in an empty void. We are one peculiar, fortunate family living in a bustling, diverse, and sometimes dangerous neighborhood. The stars are not just distant lights. They are other systems, each with its own history, its own story of chaos or calm. This is the true impact, a profound and deeply human shift in perspective. We have been humbled. We have been shown that our idea of normal was just a reflection of our own limited experience. The universe is infinitely more creative than we are. And in that diversity, the fact that a quiet, stable, and life-bearing world like ours exists at all becomes even more precious, more fragile, and more wondrous. We have travelled far on this journey. We have stood on the precipice of a new reality, a galaxy saturated with solar systems, overflowing with worlds. We have counted them in the hundreds of billions. We have found them in the just right zones where oceans could flow. We have seen that our own home is just one of countless variations, a quiet outlier in a chaotic and creative cosmos. The scale of this is almost too vast to hold in the human mind. The numbers become abstract, like grains of sand, losing their meaning. And so, we must return. We must ground this cosmic scale in the one thing that gives it meaning, the human element. Because behind all of this data, behind the telescopes and the statistics, there is a simple beating heart. It is the heart of the dreamers, the explorers, and the quiet listeners. It is the part of us that looks up at that vast, crowded sky and asks the question that truly matters. Not, are there planets? But, is there anyone else? This is the real human story. It is the story of our profound and perhaps deepest need to not be alone. It is the story of the search for a signal, for a sign, for an echo of our own consciousness in the great, silent expanse. This search has a name, SETI, the search for extraterrestrial intelligence. And the explorers on this journey are not astronauts in silver suits. They are astronomers, physicists, and engineers, sitting in quiet control rooms, pointing giant radio telescopes at the stars, and simply listening. They are listening for a pattern. Amidst the natural static of the universe, the hiss of pulsars, the rumble of distant galaxies, they are listening for something unnatural. A single, repeating, mathematical signal. A hello from across the void. In 1961, a young astronomer named Frank Drake tried to give this vast romantic question a human structure. He wrote what is now known as the Drake equation. It is not so much a calculation as it is a poem, a way to organize our wonder, It breaks the impossibly large question of how many civilizations are out there into smaller, more human-sized pieces. How many stars form each year? How many of them have planets? How many of those planets are in the habitable zone? On what fraction of those does life arise? On what fraction of those does intelligent life arise? And then, the most human and heartbreaking part of the equation. For how long does a technological civilization last before it destroys itself, or simply fades away? Depending on the numbers you put in, whether you are an optimist or a pessimist, the answer can be thousands of civilizations, or just one, us. The equation doesn't give us an answer, it gives us a mirror. It shows us that the search for others is also a search for ourselves, a reflection on our own place in the cosmos and our own chances of survival. For decades, these dreamers have been listening, and for decades, the universe has met their search with a profound, overwhelming silence. Until one night, in 1977, an astronomer named Jerry Eman was working on a SETI project, scanning data from a radio telescope. The telescope was pointed at a patch of sky, and the data was printing out, as it always did, on a long sheet of computer paper, a string of numbers representing the noise of the cosmos. And then, for 72 seconds, something appeared. A signal. An intensely strong, clear, narrow-band signal. Exactly the kind of signal an artificial transmitter would send. It was so powerful, so perfect, that Eamon, in a moment of pure human astonishment, circled the data on the printout and wrote one word in the margin. Wow! This was the moment, the human element in its purest form, the sudden, heart-stopping thrill that this was it. They had found it. A call from someone else. But the wow signal was never heard again, though astronomers have returned to that same patch of sky again and again. There has been nothing but silence. Was it a message? A glitch? A civilization that flickered and died? We will never know. And so, the silence continues. This is the great paradox, the one that grounds all of our cosmic discoveries in a deep, emotional reality. It is called the Fermi paradox. If the galaxy is full of solar systems, if there are billions of Earth-like worlds, if life has had billions of years to evolve, where is everyone? This is the human element. It is the feeling of standing in a crowded room filled with billions of people and yet feeling utterly, completely alone. Are we the first? Are we the last? Or is the distance between us just too vast to cross? We do not know. And so the human explorers, the dreamers, continue to listen. They listen out of curiosity. They listen out of hope. They listen because it is in our nature to call out into the dark and to wait for a voice to call back. We had found them. The data was clear. Kepler had shown us that the galaxy is full of small, rocky worlds orbiting in the just right zone. The human heart, so long starved for good news, was quick to celebrate. We began to imagine these new worlds as Earth twins, painting them in our minds with blue oceans, white clouds, and green continents. We had found our neighbours. The search, it seemed, was nearing its end. But this is where the true battle for truth begins. This is where our optimism meets the opposition. And the opposition, in this story, is not a person or a skeptical critic. It is the cold, indifferent, and incredibly complex reality of physics. The Goldilocks zone is a beautiful, simple idea. But the more we study it, the more we realize that it is only a starting point. It is not a guarantee of life, it is merely the potential for liquid water. And it turns out there are many, many ways for a planet in the perfect spot to become a nightmare. The battle for truth is this: a planet's habitability is not just about distance. It is a fragile, ongoing struggle, a complex symphony of factors that must all play in perfect harmony for billions of years. And our own solar system gives us two perfect examples of failure, right next door. Look at Venus. It orbits near the inner edge of our Sun's habitable zone. By all early definitions, it should be a temperate, tropical world. But it is not. Its thick, choking atmosphere of carbon dioxide triggered a runaway greenhouse effect, trapping so much heat that its surface is now hot enough to melt lead. It is a furnace. Look at Mars. It orbits near the outer edge of the zone. We see the scars of ancient rivers and lakes on its surface. It was habitable, but it failed. It was too small. Its core cooled, its magnetic field died, and the sun's solar wind scoured its atmosphere away, turning a world that once had water into a frozen, red desert. Two planets, both in or near the just right zone, two worlds that are now sterile wastelands. This is the opposition. This is the harsh truth that tempers our excitement, and this problem becomes even greater when we look at the most common planets we've found. The most numerous stars in our galaxy are not sun-like stars. They are small, cool, red dwarfs. Because they are so dim, their habitable zone is not far out, like ours. It is huddled in, incredibly close to the star, for warmth. This proximity creates two profound challenges. First, any planet orbiting that close is almost certainly tidally locked. It shows the same face to its star forever. One side of the planet is trapped in perpetual scorching daylight, while the other side is in an endless frozen night. While models suggest a thick atmosphere could circulate heat, creating a ring of twilight where life might cling, it is a far cry from the gentle days and nights of Earth. But the second problem is far more violent. Red dwarfs, especially when they are young, are notoriously volatile. They are angry stars. They erupt with powerful solar flares and bursts of radiation, far more intense than anything our sun produces. A planet in that close inhabitable zone would be blasted again and again by these flares. Over time, that relentless radiation could strip a planet's atmosphere away completely, boiling off its oceans and sterilizing its surface. So, the most common habitable planets in our galaxy might be worlds that are simultaneously tidally locked and irradiated. This is the great humbling resistance we face. And there is one final, inescapable truth. The habitable zone itself is not fixed. It moves. Stars, like people, change as they age, and as they age, they grow hotter and brighter. As our own sun has aged, its habitable zone has slowly drifted outward. Earth's comfortable, temperate position is temporary. In a few 100 million years, the sun will have grown bright enough that Earth will no longer be in the just right zone. Our planet will become too hot. Our oceans will begin to boil. We will become, in time, another Venus. This is the opposition. Habitability is not a place, but a process. It is a delicate, fleeting balance that must be maintained against all the forces of the cosmos. Against violent stars, against atmospheric loss, and against the simple, inexorable passage of time. Finding a planet in the zone is not the end of the search. It is the beginning of a much harder one. Finding a planet that has managed to win this long, cosmic battle for survival. For this entire journey, our search has been anchored by a single guiding principle: the star. We have been looking for worlds in the Goldilocks zone, a region defined entirely by the light and warmth of a parent sun. We have been, in essence, searching for reflections of our own sun-drenched existence. We have been searching for light. But what if a world doesn't need a sun at all? This is the next awakening, a realization that is, in its own way, as profound as the discovery of 51 Pegasi b. It is the understanding that the galaxy is not just a collection of bright, shining solar systems. It is also home to a vast, hidden population of dark travelers, worlds that move in the endless, frozen night between the stars. They are called rogue planets, free-floating planets, but perhaps a more poetic and more accurate name for them is wanderers, or, as some astronomers call them, orphans. These are planets that are not bound to any star. They drift alone through the galaxy, cold and silent, moving through the dark with no orbit, no sunrise, no year to mark their passage. For a long time they were purely theoretical, but as our understanding of planetary formation grew, their existence became not only possible, but inevitable. We learned that the birth of a solar system is a violent and chaotic affair. In the early, turbulent days, as giant planets form and migrate, their immense gravity interacts, reshuffling the orbits of smaller worlds. In this complex gravitational dance, it is easy for a planet, especially a smaller, Earth-sized one, to be flung away, ejected, thrown out of its home system with such force that it escapes the pull of its parent star forever. This is where these orphans come from. They are the lost children of chaotic solar systems. And there are billions of them. When scientists ran computer models of solar system formation, these ejections happened constantly. The models suggested that for every stable planet that remains in orbit, several others might be cast out. If that ratio holds true across the galaxy, then the Milky Way could be filled with a hidden population of wanderers that outnumbers the stars themselves, a vast, invisible sea of solitary worlds. But how do you find a planet that has no sun? How do you see an object that is impossibly small, impossibly cold, and drifting in complete and total darkness? You do not look for the planet. You look for its gravity. The technique is called gravitational microlensing. It is an elegant and subtle way of seeing the unseen. Einstein's theory of relativity tells us that a massive object, like a planet, warps the fabric of space around it. If this invisible rogue planet happens to pass perfectly in front of a distant background star, its gravity will act like a lens, bending and magnifying the starlight. For a brief, precious moment, the distant star will appear to get brighter and then fade in a very specific, characteristic way. From these brief, silent magnifications, we can deduce the mass of the invisible object that passed by. And we have found them. In 2011, a survey announced it had detected objects that matched the mass of Jupiter, but were not bound to any star. Later observations found signals from smaller, Earth-sized wanderers. The orphans were real. This awakening changed our map of the galaxy once again. We had to add a new, vast, and dark environment to our understanding. The spaces between the stars, which we had always assumed were empty, are not empty at all. They are home to 1 trillion hidden worlds. These worlds would be cold beyond comprehension, their surfaces frozen to just a few degrees above absolute zero. And yet, are they truly dead? A large planet, even in total darkness, generates its own internal heat from the decay of radioactive elements in its core. If a rogue planet has a thick, insulating atmosphere or a deep, ice-covered ocean, that faint internal warmth could be trapped. This is the new awareness. The possibility of internal oceans warmed not by a sun, but from within. The galaxy, we are learning, is not just a collection of lights. It is a place of profound and hidden depths. Our journey has brought us to a place of profound and humbling perspective. We have found that our galaxy is not an empty void, but a teeming metropolis of solar systems, numbered in the hundreds of billions. We have found that our normal home may be a rare, quiet exception, and we have awakened to the possibility of 1 trillion dark orphan worlds, drifting in the cold, silent ocean between the stars. With each step, our understanding of where life could be has expanded, from sun-like stars to red dwarfs to worlds with no sun at all. But now we arrive at the deepest truth, the final and most important revelation. It is a truth that redefines everything we thought we knew about life itself. The revelation is this: the ingredients for life are not special, and they are not rare. They are, in fact, among the most common fundamental materials in the entire universe. For so long, we have operated under the assumption that life is a miracle, a delicate, fragile accident that happened here on Earth because we had the perfect, lucky combination of elements. We thought life was the destination. We were wrong. The ingredients for life are the starting point. The elements that make up every living thing on Earth, the carbon in your cells, the nitrogen in your DNA, the oxygen you breathe, the hydrogen in your water, these are not precious metals. They are the simple, abundant, leftover building blocks of the cosmos. They are everywhere. And these elements, it turns out, want to be life. When we point our radio and telescopes deep into interstellar space, into the vast, cold, dark clouds where new stars are being born, we do not just find dust and gas. We find chemistry. We find complex organic molecules, sugars, alcohols. We even find amino acids, the very building blocks of proteins. This is the revelation. The ingredients for life are not made on planets. They are forged in the cold darkness of space, in the stellar nurseries before the planets even exist. These molecules then rain down onto the new worlds as they form, seeding them from day one. Life, we are learning, is not a miracle that happens to a planet. It is a cosmic process, a property that matter expresses when the conditions are right. The universe provides the raw materials. Life provides the pattern. This profound truth was not found by looking billions of light years away. It was found by looking in our own backyard at the icy moons of our own outer solar system. Our search for life was always focused on the Goldilocks zone, on worlds that felt the warmth of a sun. But then we looked at Europa, a moon of Jupiter. It is a ball of ice, far outside the sun's habitable zone, frozen in a deep cold. And yet, beneath its cracked icy crust, we have definitive evidence of a vast, global ocean of liquid salt water. We found the same thing at Enceladus, a tiny, shimmering moon of Saturn. It, too, has a liquid water ocean under its ice, and it is active. We have seen geysers of this ocean water erupting from its surface, plumes of vapor and ice crystals shooting into space. How can there be liquid water so far from the sun? The answer is the revelation. These worlds are not warmed by sunlight. They are warmed from within. They are warmed by tidal forces, by the relentless gravitational squeezing and stretching from their giant parent planets. This discovery shatters the Goldilocks zone as the only path to life. It proves that life does not need sunlight, it only needs energy. and energy can come from many places, from tidal friction, from the heat of a planet's own core, or from chemical gradients at the bottom of a dark ocean. This is the deepest truth. The galaxy is not just full of planets. It is full of ingredients, and it is full of energy. This revelation connects everything. It means that the billions of orphan planets drifting in eternal darkness are not necessarily dead. If they are large enough to have a hot core, they could have liquid water oceans hidden beneath their icy shells, warmed from within for eternity. It means that the countless icy moons we have yet to explore in our own solar system, and the trillions more across the galaxy, are all potential habitats. The search for life is not just the search for Earth twins. That was our old, limited dream. The new, deeper reality is that life is resilient, adaptable, and opportunistic. The universe is fertile, and life, in some form, may be an inevitability. It might be waiting in the dark oceans of Europa, or in the methane lakes of Titan, or on a rogue planet we will never even see. The universe is not a collection of sterile rocks. It is a living, chemical system, constantly building, constantly exploring possibility. Life is not the exception, it is the theme. We have come so far. From a single, lonely planet in a sky we thought was empty, to a galaxy saturated with worlds, we have found them in the fire of their suns and in the absolute frozen darkness between the stars. We have learned that the ingredients for life are not rare, but are woven into the very fabric of the cosmos, scattered like seeds in the interstellar wind. Now, we must pause. This is the moment for quiet, for awe. It is the moment to step back from the data, from the numbers and the charts, and simply reflect on what it all means. What does it mean to know, with scientific certainty, that our home is one of billions? For most of human history, we have defined ourselves by our separation. We were the center of creation. We were the single, miraculous exception. This belief made us feel special, but it also made us feel profoundly alone. This journey has taught us the opposite. The final reflection is not on our smallness, but on our connection. We are not separate from the cosmos. We are not spectators looking at it from the outside. We are, and have always been, inside it. You are, right now, in the Milky Way. You are not just on Earth. You are a passenger on a planet that is moving at hundreds of thousands of miles per hour in a vast, slow orbit around the galactic center. The galaxy is not out there. It is right here. The stars above you are not strangers. They are your neighbors. This is the first and most profound reflection, a shift from isolation to belonging. The second reflection is on our own substance. When we look at the stars, it is easy to feel a sense of distance, but there is no distance. The universe is not just around you, it is within you. The iron in your blood, the iron that allows you to carry oxygen to your brain to think these thoughts, was not made on Earth. It was forged in the heart of a massive star that lived and died billions of years before our sun was even born. The calcium in your bones, the carbon in your cells, every atom that makes you you, was created in a stellar furnace, scattered across space in a supernova explosion, and gathered up again by gravity to form this solar system. You are, in the most literal and scientific sense, made of stardust. You are recycled stellar matter. You are the galaxy's own material, organized in such a way that it has become conscious. And this leads to the final, most breathtaking reflection. For all of its existence, the Milky Way has been a vast, unthinking system. It has followed the laws of physics, of gravity and chemistry in silence. Stars were born, planets formed, and galaxies collided, all without awareness. And then, on at least one small planet, in one quiet corner of this vast structure, that stardust woke up. The matter that was once in the core of a star learned to see. It built eyes from those recycled atoms and looked out at the very stars that had created it. The galaxy, through us, is finally becoming aware of itself. This is the meaning. This is the quiet awe. When you look up at the night sky and you wonder, what is out there? You are not a stranger asking a question. You are the universe asking a question about itself. You are the means by which the cosmos is reflecting on its own vast, intricate, and beautiful existence. Our search for other worlds, our search for life, is not an invasion. It is a family reunion. It is the galaxy searching for itself. In all this vastness, in all this time, the number of planets and stars becomes almost irrelevant. The true meaning is found in this single, quiet connection. The atoms that make the stars are the same atoms that make you. We are not just living in the universe. We are the universe, experiencing itself. And in that reflection, the feeling of being small dissolves, replaced by a profound and peaceful sense of belonging. Our reflection has brought us home to the profound understanding that we are not just in the galaxy, but of it. This knowledge is the true legacy of our search. It is not a catalogue of planets, but a new map of home. And this new map is far grander than we ever imagined. The story of how many has left us with a new, more intimate question. Where exactly are we? The legacy of our journey is this new cosmic geography. We now have an address. We live in a barred spiral galaxy called the Milky Way, a vast, swirling city of stars, 100,000 light years across. This city has its busy, chaotic downtown and its quiet, sprawling suburbs. We do not live in the chaotic centre, near the supermassive black hole, where radiation is strong and stars are packed tightly together. Nor do we live far out on the sparse, lonely rim. Our address is in a quiet, calm and stable residential neighbourhood. We reside in a minor arm, a kind of side street, known as the Orion Spur. This spur is nestled peacefully between two of the galaxy's grand, major spiral arms, the Sagittarius and the Perseus arms. This location, our home, is a sweet spot. It is a region peaceful enough to have allowed our solar system to remain stable and undisturbed for billions of years, giving life the one thing it needs most, uninterrupted time. But our neighbourhood is not static. We are in motion. Our entire solar system, carrying Earth with it, is on a long, slow journey. We are orbiting the galactic centre, moving at hundreds of thousands of miles per hour, yet the journey is so vast it takes us roughly 230 million years to complete a single lap. The last time we were at this spot in our orbit, dinosaurs were just beginning to walk the Earth. This is the legacy. Our story is now woven into this grand, galactic migration. And our neighbourhood is not empty. We are moving through a region of space called the local bubble, a vast, hollowed-out area about 1,000 light-years across. Astronomers believe this bubble was carved out millions of years ago by a series of ancient supernovas, stars that exploded and cleared the area of dense gas and dust. We are, in a sense, travelling through the echo of an ancient, local catastrophe, which has given us the gift of a clear, transparent sky. Our city of stars, the Milky Way, is also part of a larger community. This is our extended family. It is called the local group, a collection of over 50 galaxies, all bound together by their mutual gravity. Most are small dwarf galaxies, but our group is dominated by two large spirals. Our Milky Way and our nearest major neighbour, the Andromeda Galaxy. Andromeda is our great twin, 2.5 million light-years away, but it is not standing still. It is moving toward us, and we are moving toward it. This is a profound part of our legacy, a story that lives on in our future. We now know that in about 4 billion years, our galaxy and the Andromeda Galaxy will collide. It will not be a collision of destruction, as the space between stars is too vast for them to hit. Instead, it will be a grand, slow-motion merger. Over millions of years, the two great spirals will dance around each other, their gravity tearing them apart and reassembling them into a single, new, enormous galaxy. To any future observers on this planet, the night sky will become a spectacle of unimaginable beauty. The faint fuzzy patch of Andromeda will grow, year after year, until it fills the sky, a second river of light, a sky filled with the glow of two merging galaxies. This is our new story. This is the legacy. Our home is not a single isolated planet. Our home is a quiet neighborhood in a vast moving city. That city is part of a local group of galaxies, and that group is on a path of inevitable, beautiful, and creative change. We are not just a planet. We are part of a grand cosmic narrative, a story of connection, motion, and transformation that stretches from our own backyards to the edge of the intergalactic void. We have travelled from an idea that was once heresy that stars are other suns to a scientific fact as solid as the ground beneath our feet. We have found a galaxy not of lonely lights, but of solar systems, numbered in the hundreds of billions. We have seen our own home reflected in the data, a quiet, perhaps rare, harbour of stability in a beautifully chaotic cosmos. We have learned that the ingredients for life are not a miracle, but a given, woven into the fabric of space itself. And so, after this long journey, we return to the question that started it all, the one that echoes beyond time. How many solar systems are in our galaxy? We want a number. We are human, and we are drawn to counting, to measuring, to defining the infinite so we can hold it in our minds. We want a final, satisfying answer. But the final lesson of our journey is this: the universe refuses to give us one. There is no final number. And the reason why is perhaps the most profound lesson of all. We cannot find a final number because the galaxy is not a static object. It is not a finished museum, a gallery of lights that we can simply walk through and tally. The galaxy is a process. It is a living, breathing, dynamic system that is, in this very moment, in the act of creation and destruction. The number is not a total, it is a pulse. Think of it this way. If you were to ask, how many waves are in the ocean? The answer would depend on the second you looked. A new wave is cresting, another is fading. The number is a snapshot of a system in constant motion, so it is with the Milky Way. Right now, as you listen to these words, deep in the spiral arms, in a cloud of gas and dust, a new star is igniting. A new protostellar disk is forming. And in that disk, the first grains of dust are beginning to stick together. The first seeds of new planets. A new solar system has just been added to a count that was already beyond counting. And in that same moment, somewhere else in the galaxy, an ancient star is exhausting its fuel. It is swelling into a red giant, consuming its inner planets, boiling their atmospheres away. Its story is ending. The number has changed again. This is the echo beyond time, Our search for a simple quantity has revealed a timeless quality, that the universe is prolific, it is fertile, it never, ever stops. This lesson weaves itself into humanity's ongoing cosmic journey. It tells us that creation is not a singular event that happened in the past. It is a continuous, ongoing process that is happening now. The galaxy is always recycling itself. The atoms from the star that just died will be scattered into space, enriching the interstellar medium, and will one day be gathered up again to form yet another star and another family of planets. The best answer we have, then, is not a number. It is a range, an estimate, a gesture toward the immense, hundreds of billions. We say this phrase knowing that it is both an answer and an admission of beautiful, profound ignorance. It is an acknowledgement of scale, a recognition that the cosmos will always exceed our grasp. This changes our future journey. We are no longer explorers seeking to fill in the blank spots on a map. We are participants, witnesses to a process that is larger than time. Our journey is no longer about counting. It is about understanding. It is about listening to the atmospheres of those billions of worlds. It is about searching for the chemical fingerprints of life. It is about understanding the different pathways of planetary evolution. And perhaps, in doing so, understanding our own. The final, timeless lesson is that the universe is not a collection of static, lonely objects. It is a vast, interconnected network, a living, evolving ecology of matter and energy. We are not just in this system, we are of this system. The answer to how many is not a number that defines the galaxy. It is a realization that defines us. It tells us that our solar system is not an accident. It is an example. It tells us we are a part of a pattern, a rhythm, a creative pulse that never ends. The echo of our question, how many? It is answered by the galaxy, with the quiet, steady, and unending beat of its own creation. And so, our long journey through the stars comes to a gentle close. We began with a single, impossible question. How many solar systems are in our galaxy? We hoped for a number, a finite, measurable answer to hold in our hands, but the universe has given us something far more profound. It has given us a sense of scale, a sense of connection, and a new, deeper understanding of home. The answer, we have learned, is not a number. It is an abundance. Hundreds of billions of worlds, yes, but that is a figure so vast it becomes a feeling, a quiet, meditative awe. The sky above us is not a dark, empty ceiling. It is a city of light, a teeming, living neighborhood. And we are not just looking at it, we are inside it. As you rest here, as the night deepens and your thoughts begin to drift, let this new reality settle around you. The galaxy is not somewhere else, it is here. The air you breathe, the ground beneath you, the very atoms that form your body are all part of it. When you look at your hand, you are looking at matter that was forged in the fiery heart of a star that lived and died billions of years ago. The iron in your blood, the calcium in your bones, all of it was scattered across space, recycled and gathered up again to form our sun, this planet, and eventually you. You are not separate from the cosmos. You are its continuation. You are, in the most literal sense, the Milky Way, aware of itself. This is the great poetic truth. The universe has spent 13 billion years of silent, physical evolution of stars forming and dying, of matter clustering and scattering to arrive at this moment. A moment where a part of itself, you, can rest and breathe and quietly reflect on the whole. The next time you step outside on a clear night and look up at that band of light, that faint, glowing river of stars we call the Milky Way, remember what you are seeing. You are looking into the heart of your own home. You are seeing the combined light of billions of your neighbours, their glow blurred together by unimaginable distance. And remember what is hidden in that light. Hidden in every point of brightness and in the dark spaces between are the worlds we have journeyed to tonight. The hot Jupiters, the compact clockwork systems, the lonely dark orphans, and the billions of small rocky planets in their just right zones. Each one is a story. Each one is a possibility. Our solar system is just one of these stories. A quiet one, perhaps a rare one, a stable harbour in a vast and often chaotic ocean. We are one, orbit among countless others. This knowledge does not make us small. It makes us connected. It means the processes that created our world are not unique. They are universal. The same laws of physics, the same creative chemistry that led to life here, are at play in every corner of the galaxy. We are a part of a pattern that repeats in endless, beautiful variations. So, as you drift towards sleep, let your thoughts return to the stars. Imagine our galaxy as it truly is, a vast, spinning disk of light, a spiral of creation, always in motion, always building new worlds from the dust of old ones. Imagine our sun, a single, ordinary star, one of hundreds of billions, following its long, slow path through that city of light. And on a small blue planet orbiting that gentle star, you are here, a part of that grand, cosmic story. You are a witness, you are the evidence. The galaxy does not hurry. Stars are born, planets form, and time stretches calmly across billions of years. We are part of that same unhurried rhythm. And as you lie here, resting on a planet that is part of a pattern stretching farther than the eye can see, you can feel that connection. The stars outside your window are not strangers. They are neighbours. They are suns. And they are, all of them, holding us gently in their shared, luminous and unending story. Welcome home.